In this video we're going to see how moments can be used to consider the equilibrium of some simple rigid bodies. So, a rigid body then is an object whose shape and dimensions can be assumed not to be changed by the forces acting on it. And the rigid body will be in equilibrium if and only if, first of all, the resultant force is zero, and secondly, the resultant moment about any point is zero. The condition that the resultant moment should be zero is often rewritten as saying that the anti-clockwise moments about a point must be equal to the clockwise moments about a point. So let's see this now in three examples. The first example, we have a uniform rod AB of weight 30 newtons and length 2 meters, rests on smooth supports at A and B. A load of 50 newtons is attached to the rod A. Is attached to the rod 0.5 meters from A. Find the forces exerted by the supports on the rod. So what we're going to do is we're going to start off by drawing a force diagram for the system consisting of the rod together with the load. So we've got the weight of the rod, we've got the weight of the load, and then we've got the reaction forces at A and at B. And we will add the important dimensions onto the diagram. Since the rod and the load are in equilibrium, we can say that the resultant force vertically must equal 0, which gives me FA plus FB minus 50 minus 30 must equal 0. In other words, FA plus FB must equal to 80 newtons. Then we can take moments about any point. I'm going to choose to take moments about the point A. So the moments about point A, the resultant moment about the point A must equal 0, but we're going to calculate this using the fact that the clockwise moments must equal the anti-clockwise moments. Now the clockwise moments are the 50 Newton force, gives me a clockwise moment of 50 times by 0.5 about A. And the 30 Newton force is going to give me a clockwise moment of 30 times by 1 about A. So the clockwise moments we've got are 50 times by 0.5 plus 30 times 1. The anti-clockwise moments, well, FA has no moment about A because it acts through A. And FB has got an anti-clockwise moment of FB times by 2. So the anti-clockwise moment is 0 times FA plus 2 times FB. So that gives me 55 equals 2 times FB, which gives me FB must be 27.5 newtons. So FA must be 80 minus the value of FB from my first equation, so FA is 52.5 newtons. Let's move on and look at a second example. And in the second example we've got a uniform plank AB of weight 150 newtons and length 6 meters, lies on a horizontal roof perpendicular to the edge, with the end A overhanging the edge by 2 meters. If a load of 200 newtons is attached to A, what downward vertical force must be attached to B to just prevent the plank from overturning? So we need a diagram. So there's my diagram. I've got the plank AB, I've got the load of 200 newtons sitting at A, and I'm going to need to add some forces to that. The weight of the plank is 150 newtons, and that acts at the midpoint of the plank because it's a uniform plank. We've got the weight of A is 200 newtons. We've then got the downward force attached to B of P newtons, The final force we have to add is the reaction between the roof and the plank. Now, if the plank is just on the point of overturning, then the plank is on the point of rotating about the edge of the roof. So the reaction of the roof on the plank must act at the edge of the roof in the critical case. We need to add the dimensions onto the diagram as well, so the important lengths. And now we can say that the resultant force vertically must equal 0. So the resultant force vertically, I've got R upwards, and I've got take away P, take away 150, take away 200, must equal 0. So in other words, I've got R minus P must equal 350. Now I'm going to take moments about one of the points. In this case, I'm going to choose to take moments about B, because if I take moments about B, P won't come into the equation at all. So I've only got to do the moments for the 150 newtons, the 200 newtons and the R newtons. That will give me the value of R, and then I can deduce the value of P from my earlier equation. So taking moments about B, the clockwise moments have to equal the anti-clockwise moments. The clockwise moments are given by the 150 newtons and the 200 newtons. So the clockwise moment is 150 times by 3 plus 200 times by 6. The anti-clockwise moment is given by R, and that is simply going to be R times by 4. P doesn't give us any moment at all because it's actually acting through the point B. So I've got the equation 150 times 3 plus 200 times 6 must equal R times 4. In other words, 1650 is 4R, which gives me R as 412.5, which means that P must be 62.5 newtons. Moving on to our final example, we have a non-uniform rod AB of length 2 meters is suspended in a horizontal position by 2 vertical strings, one attached to each end of the rod. The weight of the rod is 60 newtons and acts through a point G where A to G is 1.1 meters. A load of 20 newtons is placed at the point P where A to P is equal to X. Find in terms of X the tension in each string. Either string will snap if the tension in that string exceeds 42 newtons. Prove that for equilibrium to be possible, the value of X must lie between 0.5 and 0.9. So we need a diagram. So there's our rod. The weight of the rod acts 1.1 meters away from A. We've got the tension in the first string, the tension in the second string, and we have got the load of 20 newtons being placed X meters away from A. So the force diagram there shows the forces acting on the rod together with the load. Since the system is in equilibrium, we need the total vertical force to be equal to 0, which means that we've got T1 plus T2 minus 20 minus 60 must equal 0. In other words, T1 plus T2 must equal 80. Taking moments about the point A will give me an equation involving T2 but not T1, so that's a good point to take the moments about. So the clockwise moments are given by the 20 newtons and the 60 newtons. The 20 newtons has a clockwise moment of 20 times x. The 60 newtons has a clockwise moment of 60 times 1.1. The anti-clockwise moments are provided by the T2, and that is going to be T2 times by 2. So the equation we've got is 20 times x plus 60 times 1.1 must equal T2 times 2. In other words, we've got t2 is equal to 10x plus 33. t1 is 80 minus t2. And 80 minus t2 is going to give me 47 minus 10x. Now we know that the tension in either string must not exceed 42 newtons. So the fact that T2 must be less than or equal to 42 tells me that 10x plus 33 must be less than or equal to 42. So 10x must be less than or equal to 9, so x must be less than or equal to 0.9. The fact that T1 must be less than or equal to 42 tells me that 47 minus 10x must be less than or equal to 42, which gives me that 5 must be less than or equal to 10x. In other words, 0.5 must be less than or equal to x. So putting the two results together, we've got the value of x must lie between 0.5 and 0.9. And that concludes our look at how we can use moments to consider the equilibrium of some simple rigid bodies.